Okay, this is the video on the wave equation. We're going to look at frequency and wavelength in more detail. We're going to mention the required practical that you might have seen the video on our channel, and then we're going to use our equation to work out the answers to some equations. Okay, so first up, let's just try and link speed, frequency and wavelength to formulate our equation. If we have a look at this wave we've got in front of us on screen, you can see in the distance of 20 meters we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 complete waves. So the frequency of this wave is there are 10 in 1 second, so the frequency of the wave is 10 hertz. The speed of this wave, well, it takes 1 second to travel 20 meters, so we would say that the speed of the wave is 20 meters in 1 second, so it's 20 meters per second. The wavelength, well, we've got 10 waves that are equaling 20 meters, so if we say 20 divided by 10 will give us a wavelength of 2 meters. So looking at these numbers, you might be able to work out that if you take the speed, if you take the frequency and multiply it by the wavelength, you do get the speed of the wave. So our frequency was 10, our wavelength was 2, and 10 multiplied by 2 is 20 meters per second. So this is an equation that you do need to learn for the specification, and speed measured in meters per second, frequency measured in hertz, and wavelength measured in meters. Now, to apply all this, if you look on our channel for the required practical, you can see the waves that we do. We do something called stationary waves on a string, and we've got a vibration generator that moves the string up and down with some mass on the end to hold it under tension, and you see the waves being formed. And I've got a little bit of a clip just from somebody else, not from our channel. This is from somebody else doing it. The picture's a little bit better in the dark, and you can see that they've got a vibrating piece of string, and here you can see there's 1, 2, 3, 4, 5, 6 halves of a wave, so that would be 3 full waves, so that would be like 1 wave, 2 wave, 3 waves, and I think in a second they change it. If we just wait for the video to move on, they're changing the frequency now, and you're going to get a different number of waves. So there you can just see I think there's 4, 5 there, 1, 2, 3, 4, 5 halves of a wave, and now we're down to, you can probably see there's a wavelength and a half a wavelength, and then I think there you can just see nearly, there you go, that's a wavelength and a half, and then if we change it again, you can just see a complete wavelength, so there's 1 wavelength between the two. Okay, so all of this could lead us to some results, and this is what we could do. We could change the frequency, and we could count the number of waves and measure the wavelength, and we'd have 2 meters. We could change the frequency and count the number of waves and again measure the wavelength. Change the frequency that the string's moving, count the number of waves and measure the wavelength. Frequency, number of waves, measure the wavelength. Okay, so with all of that, we could work out, using our formula, we could say, well, the frequency and the wavelength, if we multiply these two together, we get speed equals frequency times wavelength, so that works out the wave speed. And you can see from my sample data here that for this that we've got from that equivalent experiment, when the frequency was 30 hertz, the wavelength was 2 meters, so the wave speed is 60. When the frequency is 45, the wavelength was 1.3 meters, 1.33 meters, so we get a wave speed of 60, etc. And we've done all that from the practical that you do need to know about, and it's called waves on strings, or waves through solids. Okay, but the main thing you need to get in terms of today is that if we increase the frequency, the wavelength decrease. So increasing the frequency, the wavelength is decreasing. This meant that the speed of the wave stayed the same, because the thing that was controlling the speed of the wave along there was the tension that we had on it, and that's beyond what you need to know for GCSE, but it's important to see how the two factors are affected in this equation. Alright, now this is quite sort of good to apply to some real life. So if 2 people talk to you from the other side of the hall or a big room, one's got a high frequency voice and one's got a low frequency voice, do you hear one before the other? Well, no, you don't, do you? If somebody shouted really low and somebody screamed, you'd hear them at the same time. Because the frequency is changing, so therefore the wavelength will change, but the speed of sound through air would stay the same. But we can change the frequency because the wavelength changes as the frequency changes. Okay, so that's the general idea. Now all of this, as we say, leads to our equation that you need to know. Speed equals frequency times wavelength. Some common things here you need to remember is 1 kilohertz is 1,000 hertz, a kilometre is 1,000 metres, 1 kilometres per second is 1,000 metres per second. I've put it in the triangle. Some of you might like to use the maths triangle. So if you're working out wave speed, if you cover at wave speed, you can say that wave speed is frequency times wavelength. To work out frequency, it's wave speed divided by wavelength, and to work out wavelength, it's wave speed divided by frequency. So if we do some very quick questions just to finish up, the speed of a sound wave in air of frequency 660 Hz and wavelength of 0.5 meters, well, speed equals frequency times wavelength, gives us 330 meters per second. The speed of sound wave in air with a frequency of 1 kilohertz, that's 1,000 hertz, and a wavelength of 0.33 meters, well, that's 1,000 times 0.33, which is 330 meters per second again. You should realise that the speed of sound in air is a constant. We'll come to that in the next lesson, I think. An elephant makes a noise while sleeping with a frequency of 20 hertz, so a low frequency. The sound has a wavelength of 16.5 meters. What is the speed of this wave? Well, you could say speed is frequency times wavelength, so again 330 meters per second. It's the speed of sound in air. The speed of sound in water, given that 0.2 kilohertz, which is 200 hertz, has a wavelength of 7.5 meters. Speed equals frequency times wavelength, so we've just done that, okay, 1500 meters per second. So the speed of sound in a solid, the speed of sound in water is much faster. Let's do a trickier one. The wavelength of a sound with frequency 30 kilohertz, that's 30,000 hertz, with a speed of 1,500 meters per second. Well, we can now rearrange the formula and say that wavelength is speed divided by frequency. We've changed our numbers and it's 0.05 meters. And then finally, light from the moon takes 0.8 seconds to travel 240,000 kilometers to Earth. It has a wavelength of 0.0000007. What is the frequency? So first up, let's do our speed. Well, we know the speed is distance divided by time. So the distance is 240,000, the time is 0.8 seconds, and we get a speed which is 3 times 10 to the 8, or 300 million meters per second, which is the speed of light. We can now work out the frequency. The frequency is the speed divided by the wavelength, and we get an answer in standard form of 4.3 times 10 to the 14 hertz. Now on the higher paper, in the higher questions, you will be expected to handle large and small numbers, so you need to make sure you can put these into your calculator successfully.